To start class? Yeah. Since we lost our notes, I have already uploaded like a completed version of the notes, just so we didn't lose everything we did in class. But I also don't quite remember where we left off in 5.1. I know we talked about the summation formulas, but I don't know if we actually started this example. Does anyone know? Confirm from your notes, like where we ended.
We did that one, and then we did some like summation, the sum and power of integers.
Okay, so we talked about those,
Oh yeah.
and then
we started it.
and
We didn't.
so we started this.
Yeah, we wrote it out in there.
We started that example. Okay. I'm not sure how far we got into it, so some of this might be redundant.
We're just barely on the right side.
Okay, so it says evaluate the left-right midpoint Riemann sums for x cubed plus 1 on the interval 0, 2 using 50 subintervals. So this is the n is equal to 50. We're using 50 rectangles to approximate the area. What is consistent whether we're dealing with the left, right, or midpoint Riemann sum is delta x. So this delta x is the same in all three of these. So we'll compute, I believe we computed delta x first because that's going to be used in part A, B, and C. And we said, so we found delta x to be b minus a over n. And remember, a and b are the interval that's given to you. So this is our interval AB, and n is equal to 50. So b minus a over n gives us 2 minus 0 over 50, or 1 over 25, as our delta x. And then so once we have delta x, then to look at the right Riemann sum, it's probably worthwhile to write the definition down. The Riemann sum is, and this Riemann sum is for all three of those. So if we say the Riemann sum is defined as the sum from k equals 1 to n of f evaluated at x star sub k times delta x. That's always our Riemann sum. What changes is if we talk about the left Riemann sum versus the right Riemann sum versus the midpoint Riemann sum, what's changing in that definition is this x star sub k given by one of these three things here. Is everyone clear with that? The f of x star in the sense of an area, what did that give us? What was the f of x star? Like, just in a really general sense. So yeah, the area under the curve. In particular, like what is f of x star sub 1? What would that give me? So yeah, the grid points were the endpoints of each rectangle. The x stars were the place, the x value in each rectangle that I used to determine the rectangle's what? Height. Yeah, the f of x star. So f of x star sub 1 is the height of the first rectangle times its length. That's the area of the first rectangle. So the f of x star is the height of each rectangle, and the delta x is the width of each rectangle. And again, all we're summing is a height times a width. So this area plus this area plus this area plus this area 50 times gives us the approximate area. Okay. So then in part A, we're asked to compute the right Riemann sum. I'll just abbreviate Riemann sum. And so then we're saying that, okay, I'm using the right grid point for each subinterval to determine the rectangle's height, each rectangle's height. So each x star sub k can actually be computed as one thing. We don't have to think of it as these individual one-off cases. We can say that every right grid point will be defined as a plus k times delta x. And what that actually means for us is we have these values. So the x stars for this particular setting, we start with a. That's the starting point of the closed interval. So the a is 0 plus k. And k has to stay as k is, because remember this is x star sub k. It's more or less a function of k. Times our delta x, which we said was 1 over 25. So right Riemann sums, every right grid point is defined as k over 25. So the first endpoint of our first rectangle is 1 over 25. Or sorry, the place we're evaluating in our first rectangle. So our first rectangle goes from 0 to 1 over 25, right? Because that's our delta x. And then what we're saying is to determine the height of the rectangle, we're going to use this value here on the function. The next one would be delta x, whatever the function looks like. But then we go over another 1/25th. So we have 2/25ths. And that x value is what we're plugging into the function. You know, our function's doing something like that, whatever. And then the next one is 3 over 25, the next one's 4 over 25. So it gives us all of them. And what we have to do with our x star, according to the definition of the Riemann sum, is that we have to plug our x star into the function. So then we're going to take our k over 25 and say that since f of x is equal to x cubed plus 1, x cubed plus 1, then f evaluated at our x star is really f evaluated at k over 25. Is everyone with me? It's really all we're doing is fitting in this definition of what the Riemann sum is. The only thing that changes are the x stars as we look at left, right, and midpoint Riemann sums. So there's our f of x star. Let me skip this over. So this is f of x star sub k is f of k over 25, which is equal to the input cubed plus 1 is what our function does. So f of x star is f of k over 25, which is k over 25 cubed plus 1. So please keep in mind, when we compute the Riemann sum, it's the sum from k equals 1 to n of f of x star sub k. Right, this k operates on this k. So what you get out of f of x star, it needs to be summed up. We see that we have a thing that involves k, but if this plus 1 doesn't involve k, that does not mean we can just scoot the plus 1 off to the side and not sum that up as well. This is a direct result of f of x star, so we have to sum up k over 25 cubed plus 1. That has to stay in front of the summation. The thing that doesn't necessarily have to stay in front of the summation is delta x. Because delta x doesn't involve a k, the sum doesn't necessarily operate on delta x every time we increment. But the f of x star whatever you get out of that, it always has to be in front of the summation. All right, we have our f of x star, we have delta x, so all we have to do is now sum that stuff up. So we're summing from k equals 1 to n, and again our n was 50. We're summing delta x times this expression here, k over 25 cubed plus 1. And let's just go ahead and rewrite f of x star once more. So it's k cubed over 25. Let's write it as k cubed over 25 cubed plus 1. So that's the thing that has to stay in front of the summation. We have to sum k cubed over 25 cubed plus 1. And then multiply by our delta x. So I'll just rewrite the definition out again so we can see. What each piece actually is. Is everyone all right with where we're at? Are there any questions? So notice again, what we have is this expression in parentheses for k. That thing gets summed each time, 1, 2, 3, all the way to 50. But the 1/25th is just multiplying every single term. So it's just like writing, if I wrote 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, etc., then the 2 is just multiplying the sum. So we could factor out the 2 from the sum and just say it's 1 plus 2 plus 3 plus 4 and still have the same result. So that the way that 2 is acting here is the way that this delta x acts in that summation. So, we could, if you wanted to, you could say that it's equal to 1 over 25 delta x times the sum. I'm just going to putting the parentheses around there just to let myself know that those two things have to stay in front of the summation. And so how do we sum this up? Well, we're just going to use a calculator. And then once we talk about how to find the exact area, then we can use our hands to do that. But I did link a summation calculator here under announcements, and it's just Desmos. So the thing to be aware of is that their sum is predefined as n. So instead of writing out like our definition has k, we're just going to replace our k's with the n's. It's the same thing. Oops. So we're gonna sum this up, and again, this 1 over 25, it can be out in front of the summation. So there's our delta x. Make sure it knows that we're multiplying this. Okay, so we're summing k cubed over 25 quantity cubed there, plus 1. And so we'll just have the calculator tell us what that is. It's 6.1616. And so what is 6.1616? What is that number? Yeah, it's kind of close to 2 pi. Yeah. What is that? What is it actually telling us?
The area.
Yeah, the approximate area using right Riemann sums and 50 rectangles. So if I took the graph of x cubed plus 1 from 0 to 2, and I filled that region up with 50 rectangles, no, it's not 50 of course, but, and then I use, for each rectangle, I use the right value to determine its height. You know, I have all these rectangles in here like this, etc. I'm saying approximately the area using that particular approach is 6.16. Okay, so are there any questions on that? It's really crucial that y'all are understanding how this Riemann sum that we have here is constructed, because we still have to work with that. The only observation that we've made is, in order to make an area exact, we're not going to use 50 or 100 or 1,000,000 rectangles. We're just going to let n approach infinity, and then we'll have an exact area. But we still need to be able to construct the Riemann sum and let n go to infinity. So does anyone have any questions on what we've done there?
Is the Riemann sum essentially equating to k from your original equation? A plus k times delta x?
No, because that's just a tiny component of the Riemann sum.
Right.
The Riemann sum itself is this whole thing. So it's
Oh, okay. Gotcha.
Yeah. So that k just tells us within each rectangle what value we're using to determine the height. But we have 50 of those here.
Okay.
Yeah. Any other questions? And so we have a very similar approach whether we're dealing with right, left, or midpoint Riemann sums. Remember, the only thing that changes is that x star. So when we look at part B and do the left Riemann sum, the only difference is that the x star sub k is defined as a plus k times, plus k times, k minus 1 times delta x. I'll write delta x first. So for any left Riemann sum, that's how we're determining what those x stars are. And so again, just filling this out for the information we have. Our a was 0, our delta x was 1 over 25, and k minus 1 is just k minus 1. So you're going to clean that up and say that that's k over 25 minus 1 over 25.
Is it better to break up the fractions?
So is it better to break up the fractions or just leave it as 1/25 times k minus 1? I think it's just a matter of preference.
Okay.
Once we start actually computing limits at infinity and using certain formulas, I think it's more conducive to like break things up into individual pieces.
Okay.
But if we're gonna just end up putting this in front of a summation calculator anyways, it really doesn't matter what the expression looks like. Okay, let's write this down and I want to pause for a moment. But this is our x star, so then what does our left Riemann sum look like? It's the sum from k equals 1 to 50 of what? So we don't, remember, we don't sum up just the x stars, right?
It's the 1 over 25 times.
Yeah, we don't just sum that up. We wouldn't put k over 25 minus 1 over 25 in front of the summation because we have to first evaluate the function at x star. So we're evaluating f at k over 25 minus 1 over 25 times our delta x, right, times delta x.
And isn't it the cubed plus 1?
Cubed plus 1, right. So we have our delta x times the sum from 1 to 50. And again, f just takes the input, cubes it, and then adds 1. So there's our function applied to our x star here. So that is the left Riemann sum. From here, we're just going to put that into a calculator to see what its value is. So 5.8416. You won't have to compute any of these on the final because you don't have not everybody has summation calculators on their calculator. So 8416. Again, approximate area using 50 rectangles, and the left endpoint of each rectangle is determining the height of all of the rectangles. So, you know, just a few rectangles in here. We've got 50 of them. But we're just saying like each left endpoint of every rectangle is used to determine the approximate area. So then you see we get these kinds of rectangles in here. So we're missing area under the curve, and when we looked at the right Riemann sum, we were actually computing area above the curve. So we would expect this to be an over approximation. We would expect this to be an under approximation. So do y'all have any questions at this point? Okay. I do want to go back to part A, just to show you that you can compute this stuff by hand. Oh, I already had space for that. I'll go ahead and clear that out. I already did that. Just so we can see that this was our right Riemann sum. Okay, and I probably don't have a preference at this time, but we'll put the 1/25th of delta x out in front of the summation. to sum that up. So we just threw that into a calculator, but we can compute this by hand. Using the summation theorem on the 2 pages back, Theorem 5.1. So just kind of in preparation of using this theorem, we have k cubed over 25 cubed plus 1. So what we're going to end up actually utilizing here in this theorem is we're going to use k cubed, because we've got a k cubed in our sum, and what else? What else do we have to sum up? The plus 1, right? Because see, the sum's attached to both of these pieces. So the first sum involves the k cubed. The second sum involves the 1, which is a constant. So we're going to use that first one as well. So we have to utilize both of those to compute that particular sum by hand. And the way we do that is we're just gonna kind of whittle this down so that it's recognizable directly applied to that theorem. So our 1/25th still out here. We're going to distribute the summation to both terms in parentheses, or whatever you get from the f of x star. If you had like 5 terms, the summation applies to all 5 terms. Here it's just 2. Okay, so applied to the first term, plus the summation applied to the second term. And again, the first term here, the summation from 1 to 50, from k equals 1 to 50, only affects the k cubed. So the 25, the 1 over 25 cubed here is, again, in this particular sum, it's just another constant that we can pull out in front. So we're going to take this. We're going to take that and just put it in front of this summation here. So we just have the sum of k cubed and then all of that times 1 over 25 cubed. The second summation, the plus 1 from 1 to 50, that's already in a form we can apply the formula directly to. Let me scoot this down. And that's all we've done there. So we still have that, all of that times our 1 over 25. Our delta x. Does anyone have any questions? So the only reason we're distributing, if you will, distributing that summation across all of our terms is because our summation formula only involve one thing in front of the summation. It's not the sum of something plus something else. It's just one thing. So we've distributed the summation across the terms, and this is what we're looking at. I think it's a matter of choice at what point you deal with the constants out in front of the summation. I think maybe we can just go ahead and deal with those now. This 1/25th is going to multiply here and is going to multiply here. So we now have 1 over 25 to the fourth times this sum from 1 to 50 of k cubed plus 1 over 25 sum from 1 to 50 of 1. And so we're going to now utilize that theorem. The sum from 1 to 50 on k cubed, what would that look like according to the theorem?
50 squared times 51 squared all over 4.
50 squared times 51 squared all over 4. Do y'all agree? So we have end the place we end at, right? 50 squared, here's 51 squared all over 4. Okay, so that's what that sum turns into. It's still multiplied by 1 over 25 to the fourth. Plus our 1 over 25 here times this summation turns into what? The sum from 1 to 50 of 1. 50 times 1, right? That's the constant one here. The sum, we're summing 1 from 1 to 50, so it's just n times the constant, 50 times 1 for us. So that's our hand computation. It's this number plus this number equals to 6.1616.
Let's be on the test.
Yeah, you would have to, there's a formula that's sort of, that's not in our textbook that makes this a little bit easier. But one way or the other, you're going to have to remember either the summation formula provided in our textbook or the summation formula that I'll hand out later.
Okay.
And the summation formula that I'm going to hand out later, I think it's a whole lot easier than this right here.
By the summation formula, you're talking about the theorems?
Yeah.
Theorem problem, right?
Yeah.
Okay.
You'd either remember that or you would remember the thing I'll hand out later.
Okay.
Yeah. And for us, the only way this is showing up on the final is in the exact sense. So as far as finite sums go from 1 to 50, from 1 to 1,000, like that's really not applicable to us in the long run. Okay, if you want to, figure this out on your own, you can just plug that into your calculator, but it should be 6.1616. Do y'all have any other questions on this? And then finally, the midpoint Riemann sum. Let me fit this in here. Midpoint Riemann sum, then our x star sub k is a plus delta x times k minus a half. So again, for us, a is 0, delta x is 1 over 25. Times k minus 1/2. Before we actually sum that up, what do we need to do? Where does x star go? Into the function. So again, don't just sum up that. This now gets plugged into the function. And this is where I think, like, you know, maybe distributing could be a little bit more clear. But we are evaluating that quantity cubed plus 1 by the function. Remember, that's the f of x star. That's the expression that has to stay out in front of the summation. So the Riemann sum is the sum from 1 to 50 of all of that stuff, cubed plus 1. So we have to sum all of this up. So there's the sum of f of x star, and we need to multiply all of it by delta x. So you've got to make sure you're putting these things in correctly, because some of these things are kind of like self-referred, right? Like delta x is really in there twice. So just be really clear on how that formula, the Riemann sum, is actually constructed. Do y'all have any questions on what we have here? So we need to sum that up as well. What do we have? Look at this. K over K minus a half, or n minus a half. We'll just go ahead and close those parentheses. But okay, so there's our x star. Input is cubed, and then we add 1 to it, all in front of the summation, times our delta x. So 5.99, 3 nines and a 2. That's the midpoint approximation for the area under x cubed plus 1 using 50 rectangles. So we had 3 computations. So what might you expect the exact area to be?
6.
Probably 6, yeah. So we'll talk about how to do that in the next section, how to find the exact area. But that's all for 5.1. Do you have questions on 5.1? It's very tedious. None of it actually directly, none of the things we've computed here would directly show up on the final, but there's certainly homework questions involving that. And I think you should do those because it's going to develop, you know, the fundamental nature of what we're actually doing. It's kind of unfolding in front of our eyes. Yeah, the symbols and the notation are kind of cumbersome, but again, at the end of the day, you're just taking a region, putting rectangles in it, finding the area of each rectangle, and then that's the approximate area. That's all we're doing here. It's just kind of obscured by the notation, I think. In 5.2, we're going to look at definite integrals. As opposed to, remember in 4.9, we looked at antiderivatives. Or we kind of loosely refer to those as indefinite integrals. So we have an indefinite integral, gives us an antiderivative. What does a definite integral give us, is what we're going to look at. All of the examples we looked at in 5.1, they were all functions that were above the x-axis. And we were just finding area bound by the function and the x-axis. And since all of those functions were above the x-axis, the area we found came out to be positive. But as a more general sense, if our function lies below the x-axis, like this first one here, then the area would come out to be negative. But it doesn't make sense to have a negative area in that particular context. All this is saying is that we've got an area of 6.625, and since it's negative, it just means it's below the x-axis. That's all the negative there means. We're not technically saying we have a negative area, right? It's like velocity being negative 60 miles per hour. You know, it's indicating both a magnitude, an area, and a direction. And depending on where we looked at that particular function, it looks like it's 1 minus x squared. That's just on the interval from 1 to 3. That all of that area is negative or below the x-axis. If we looked at the interval from 0 to 3, we would have some area above and some area below. So what we get, as if we're going to think about that as what's the total area, it's the area that's above minus the area below. And what that gives us is a net area. It's like this stuff here is your income, and this stuff in red is the taxes they've taken out. You get a net paycheck at the end of the month or the end of the week or whatever. So in general, when we compute an area on a function from like 0 to 2 or from 10 to 15, without looking at the graph, we can't know whether it's all positive, is it all negative, is some of it positive, is some of it negative. We're not going to really worry about that. What we're going to say is if I compute an area like this, then I'm just going to say the area from A to B, whatever that number comes out to be, I'm just going to say as a general thing that represents the net area on that function from A to B. So that's our definition here. The region R, bounded by f of x, between the x-axis, x equals A, and x equal to B. So for all intents and purposes, you could think of this figure here that's directly above. The net area is the sum of the areas that lie above the x-axis minus the sum of the areas that are below the x-axis. And here, when they say area, in this definition, area is a positive quantity. Let's just tie this into what we were talking about in 5.1. When we compute Riemann sums, so Riemann sums, in general, we're just assuming that we're not going to look at the graph for any of these. In general, we say that the Riemann sums give us a net area. We saw from that last section that Riemann sums were approximations, so we get an approximate net area whenever we compute a Riemann sum. So we'll look at a couple of examples later, but you might see a figure that's already graphed for you. And it might say that, from 0 to 3, that area is 5, and then from 3 to whatever this is, from 3 to 12, this area is, 17. So what would the net area be for this? Negative 12, yeah. The net area is the sum area above. Let me write this in a different color. Minus the area below. So, you know, if you want to think of it like if that's property, if that's your property and there's a river or something, a fence, then I have more area on the south side of that fence than I do on the north side of my fence. That's kind of an interpretation of what that's saying. But if we were to compute this, like the area, if we were like putting a Riemann sum on the area from 3 to 12, and we computed all of that and we summed it out, then the answer would come out to be a negative 17, indicating that the area is 17, but the region we're dealing with is below the x-axis. Does that make sense? So I'll just say that here. If we compute our Riemann sum, on the interval from 3 to 12 would be negative 17. So that would come out in the computation. Yeah.
And if we computed the Riemann sum from 0 to 12, it would come out to be negative 12?
Yes.
Okay, cool. So the math just bears it out. We
Yeah,
don't have to
exactly.
do any, okay.
Riemann sum on 0 to 12 would be negative 12, and the Riemann sum from 0 to 3 would be 5. Okay. Any other questions on this? So then what we're going to go into is what are these things, what do Riemann sums look like when we're talking about an exact area and not an approximation to the area. So how did we mentioned this, how do we make our Riemann sums exact? What do we have to do?
We gotta treat them like a limit and have n approach infinity.
Right. So if n approaches infinity, what does that mean? What does n represent for us in 5.1?
The number of rectangles.
The number of rectangles we're actually putting under the curve, right? Subintervals, right? So we have to, in order to make that an exact instead of an approximation, we have to fill up the region with infinitely many rectangles. So we're going to let n approach infinity, that is, filling up the region with an infinite number of rectangles. Intuitively, does that make sense? I mean, intuitively, you might think, well, you can't really fill it up with infinitely many rectangles, right? But that's why the limit's there. It's just saying, as we approach infinity, we can approach infinity all we want. You'll never get there. But if we could get there, the limit as we approach infinity will be the exact area, is what it's saying. So in theory, if we could find the exact area, that's what it's going to be, whatever we compute it to be. And so the n going to infinity, all we've got to do then is take the Riemann sum from k equals 1 to n of f of x star sub k times delta x. That definition we worked with in 5.1. All we've got to do there is then put a limit at infinity in front of it. So this will give us our exact net area. That's it. So just illustrating that with a figure. Here's 75 rectangles on the left. There's infinitely many rectangles on the right. So our approximation versus the exact area is there. Scoot down. So then we have the definition for a definite integral. What is a definite integral? The definition is you've got a function defined on a closed interval AB is integrable, and that's comparable to the word differentiable. When I say a function's differentiable on this interval, that means for the derivative is always defined for all x values on that interval. Integrable means that the integral here we see is defined for all x values in that interval. If the Riemann sum, this is our Riemann sum right here. If the Riemann sum exists and is unique over all partitions, over all subintervals or rectangles, and then the limit of the Riemann sum that we just wrote down above, the limit of that Riemann sum is going to then turn into this notation for us. So when we write out, okay, let's back up. They define this in terms of delta approaching 0. We defined it in terms of n approaching infinity. So let me just back up for a moment. It's exactly the same thing. And we can see that here. If I fill this region up on the right, this region, if I fill that up with infinitely many rectangles, what's the length of each rectangle going to be? It's pretty much 0, right? Because to fit more and more rectangles in this region, they have to be slimmer and slimmer, right? So saying n approaching infinity and the width of each rectangle approaching 0, it's the same statement. If I'm filling a region up with infinitely many rectangles, then they have to be virtually 0 in thickness.
If you plug infinity into that original delta x equation, though, don't you get infinity over infinity?
Which one? The definition here?
Like your b, was it b minus a over number of subintervals from 5, 1? That's what we use for delta
Oh
x,
yeah, okay, right. So if we say delta x is b minus a over n,
like infinity minus 0 over infinity.
but if n is approaching infinity, then wouldn't this be 0? Right, we've got a fixed numerator, the denominator gets larger and larger, the fraction gets smaller and smaller.
Can you determine that though if you also have an infinity in the numerator? Is that possible? Wouldn't you need a constant of some kind in order to determine accurately that it's approaching 0?
If it were, no, because if it were infinity over infinity, then it could have any value, right?
Right.
It's only because it is a constant on top and an infinity on the bottom that it approaches 0.
And it's always a constant on top because it's a closed interval.
It's always a constant on top because we're always saying, like, look at the area from 3 to 7. It's always, that constant there in that instance would be 4.
Oh, okay. I was assuming that
Yeah.
you're. Okay, no, I got you. I was assuming that that your n that you were saying that the n value was infinity.
Okay.
Like you were approaching n to some infinitely x value.
Okay. I see,
Infinite
I see.
x value. We were then evaluating the area under
Okay.
that line.
Okay.
You know what I mean?
Yeah,
That's-
you can do that.
That's where I was thinking, like, well, in that case, you'd have infinity over infinity, which would
Okay,
go
yeah.
back to what's his face.
That would make sense, L'Hopital.
Yeah.
That guy. Yeah, but I mean, we see this, right? If n goes to infinity, then our delta x has to approach 0.
Right, okay.
So their statement where they say delta is approaching 0, that all they've done is say that, well, we're going to define delta is the maximum possible value of all of our delta x's. Just to ensure that if the largest one is approaching 0, then all of them are approaching 0. Because I know for us what we said was delta x is always the same length across the region, but in fact it doesn't have to be the same length. So in a more general sense, if the largest one goes to 0, then the other ones smaller than that have to also go to 0. So instead of thinking about delta approaching 0, computing that limit, just replace that with n approaching infinity because it's the exact same statement. So limits at infinity do come back to compute definite integrals. So I'll just rewrite that in a moment. But that's what we're saying is that this limit as n approaches infinity on the Riemann sum, when we write that out, what that actually means is the integral from a to b on f of x dx. So this definition is as important as the definition of a derivative. The derivative h approach to 0, and the definite integral, we've got something approaching infinity. But both of those pillars of calculus are defined in the sense of a limit. Okay, so that's this notation. The integral from a to b of f of x dx means the infinite sum is all that means. This elongated, this integral sign actually came from, old books, or Leibniz or Newton's. I think it was Leibniz notation, but he would use this as an elongated s to mean an infinite sum. So for him, when he wrote down elongated capital S, to him that indicated that's an infinite sum, and that's sort of the notation that stuck as our integral notation. Because we explicitly see that when I compute an integral from a to b on a function with respect to x or whatever, that it is an infinite sum, right? If n is going to infinity, then I can just write this sum as, maybe it has less meaning like this, but it's an infinite sum regardless of how you look at it. Okay, so the components of the definite integral. And again, definite integral, what we mean is this thing here. The A and B are just the endpoints of the region. We look at a region on A to B. It's the same A, the same B. Here in the definite integral, we call those the limits of integration. We'll talk about how it like equates as well to the infinite sum. But, the function is just the function. F of x is f of x. The dx is analogous to your delta x in the summation. So the difference is that delta x was this discrete change, right? The width of each rectangle was 5, or it was 1/25th, or they were all 1/50th, or whatever it was. It was a discrete kind of change in the x values from one rectangle to the next. This lowercase dx is just like we saw with the limit going to infinity. Those are indicating just an infinitesimally small width of each rectangle. It's virtually 0, but it is still kind of analogous to the delta x in that respect. Okay. And so when I look at this sum, what did we say that this sum was? What did we just say that infinite sum gave us?
Exact.
The exact
Area.
area. What kind of area? The net area.
Yeah.
Right, so that Riemann sum is the exact net area, and so is this symbolic stuff on the left. When we compute a definite integral, what it's going to give us is the exact net area from A to B. Okay. Because we just replaced this symbol with our infinite sum stuff. It's a little more technical than that, but that's the basic idea. I'm going to write a couple more things down. I just want to finish this, the definition, so we know what we're looking at before we take a break. So that's kind of what we have with that particular notation, the integral from a to b f of x dx, kind of what that is. And then looking at the definition, we don't know how to compute this, right? We might suspect that since it's an elongated s, it might be related to an antiderivative that we did in 4.9 because they share the same symbol. But at this point, other than them sharing the same symbol, there is no indication to us that to compute integral from a to b f of x dx would involve an antiderivative. There's nothing that's telling us that at this point. So if you already know how to compute that, that's great. But at this stage in our development, the only thing we know is that they're the same symbol. I mean, they're similar symbols, right? We have a definite integral from a to b, and then we had the indefinite integral. So both of these involved f of x dx, but one actually has numbers, the other one didn't. We know for sure that this is an antiderivative. We don't know for sure how to compute this yet. Or we know how to compute it because it is just this infinite sum here, which we computed in 5.1 as a finite sum. But we have no indication that to compute it, it is related at all to an antiderivative. So that's kind of where we're at with it. Since this integral from a to b f of x dx is the same thing as the limit as n approaches infinity on the sum from 1 to n of f of x star sub k times delta x. We've kind of mentioned some of this and saw it unfold in 5.1, but when we computed the f of x star sub k, times our delta x, what we ended up with there is virtually a function of k. Or a function that involved the variable k. But once we applied the sum to that from k equals 1 to n, and think about that one we computed by hand. Once I apply the sum from 1 to n to that function of k, what does that turn into? Is it still a function of k? Or is it a function of something else now, once we apply the sum to it? I think it was on the next page here. So in this example, when we had a function of k in front of the summation, and then we applied the summation to that, it turned into this thing here, right? Or more generally speaking, this function of k, particularly in this example, the function of k cubed in front of the summation from 1 to n actually gets turned into an expression involving n, or a function involving n, right? So once we sum this f of x star sub k delta x, again, that piece right there alone is the function of k. When we sum that from 1 to n, the whole thing turns into a function of n. Does that make sense? I mean, it'll be clear when we compute stuff, but I think it's important to look at it sort of abstractly and to see what we're actually dealing with. Function of k turns into a function of n, and then the only thing left to do is compute the limit at infinity, the limit as n approaches infinity. On all of this stuff, which is a function of n. And then once we do that, you have the exact area. And having the exact net area. And then this thing right here that we're computing is the same thing as computing this thing. So that's, I guess, all of that stuff equals that thing, is what we're computing. And we'll look at specific examples, of course, but that's kind of how we're constructing those things to get an exact net area. Do y'all have any questions on any of that? Okay, so we'll take a break.
Pretty rad, like, just book a bunch of flights, and they're like, what are you doing? Like, haha, trips on you. Stop this one. What was it, Dustin Hoffman, remember that one on Outbreak? Sharon Stone is Dustin Hoffman. It's like, yeah, these people can't breathe, they're not solving fire cases. Moving it down or whatever.
The only thing that I'm confused
I need people who
about
know
is,
90s references.
I'd be able to
Yeah.
see EA or.
Yeah, it's been since the 90s since I've seen that.
Yeah. Like some,
Well, I was talking to
some
my
monkey was like caught in Africa or something.
Yeah.
Someone made it a pet, and then it like bites the kid and runs away, and the
Well,
whole
he has
town
an
like
Asperger's.
dies. Yeah.
Y'all ready?
But like the
It
only
was like
difference is
the
that
4 zombie movies. They just made people scared of real diseases.
So then, this is when we look at this definition for what a definite integral actually means. Remember, this is the limit as n approaches infinity. So the upper and lower limit of integration, those just correspond to the interval that you're looking at, the closed interval from a to b. F of x is the same thing as f of x star over here in the summation. Dx, as we said, was the same thing as this delta x. This delta x sub k is just a more generic notation. But if we're finding the area here, for instance, that these rectangles don't necessarily have to be the same width. We can still approximate the area, using differently spaced or different thicknesses for those. So, like, for instance, for example, if we have the limit as n approaches infinity on this sum here, on the interval from 1 to 3, what that actually means when we compute this limit on that interval, it's the same thing as computing the integral from 1 to 3 on our function that's a function of x, not of x star sub k. So 3x squared plus 2x plus 1, and delta x is dx. So that if we compute that sum, it's the same thing as computing that definite integral right there. And for now, what we're going to do is, if it says evaluate the integral from 1 to 3 on 3x squared plus 2x plus 1, what we're going to do is we're going to actually turn it into this sum, evaluate the sum as a function of n, and then take the limit as n approaches infinity. That's how we're going to evaluate that. Using the definition. Before we actually look at using the definition, we're going to look at some definite integrals that we have other means to find the area, where we don't necessarily have to write out the summation and compute all of that. So does anyone have any questions on the comparison or the differences between our infinite Riemann sum and the definite integral piece? All right, so then we'll look at a few definite integrals. We could compute all of these using the definition, but we're going to use geometry to evaluate each one of these. And even if you progress in calculus, and even some in this class, if you can use geometry to evaluate, it's honestly a much more efficient means than finding computing the infinite sum, or as we'll see later, computing this stuff by hand, we'll say. So in order to evaluate it by geometry, you need to kind of draw it out. We're going to draw the function 2x plus 3 on the interval from 2 to 4. So our y-intercept of 3 and a slope of 2. And we're only concerned with that line from an x value of 2 to an x value of 4. So we'll just say that's here and here. So then what we're saying is from this x value of 2 to the x value of 4, what's the area bound by the line x equal 2, x equal 4, and the x-axis? So that's a figure we can just geometrically determine the area of that figure. There's actually a formula to compute the area of those. How would you compute the area if you didn't know the formula?
You chop it so that you have a rectangle
Yeah.
and a triangle.
Right? We'd say, all right, well, what's the area of that rectangle plus what's the area of the triangle? Oops. But the area of these things is side A, another side B, and whatever the base is H. However you want to label that. The area of those types of figures is 1/2 the base times the sum of the two sides. Is the area. So whichever one you prefer to use, we have to use here. So to compute this definite integral, what it means is it's saying what's the area bound by this function from 2 to 4 and the x-axis. So we're going to find that area Okay, well, the base length 2. What's the height of each side? What's the height of the left-hand side of this figure?
F of 2.
F of 2, right.
So it's 7.
So it's 7. This is an x value of 2. The height of this thing is f of 2. So that's a height of 7. What's the height of the other side? F of 4, which is, huh?
11.
Yeah, 8 plus 3, 11. Here. It's here. So then we can compute the area, consequently compute the definite integral. So that definite integral then is equal to 1/2 the base times the sum of the two sides. So when we evaluate that, the exact area of that figure, or the definite integral, is equal to exact area is 18. Not all functions create a geometric shape that we can do this with, which is why this method is limited. We've already seen a few like x squared, x cubed plus 1. Those don't generate a geometric figure where we could just use geometry. But when and if that happens, it's going to be a much easier computation than other methods that we look at. Okay, so does anyone have questions on that? Yeah.
So I thought, shouldn't the h be our base? Or no? I thought like h should be our height.
Okay, yeah, you could put it there if you want. It's kind of arbitrary at that point. We could call this h. We could call this, s, and we could call this b for base. And look at it that way. Yeah. If that makes more sense to you. Okay. Okay, so the next one here. Integral from 3 to 4. So the function is the square root of 1 minus x minus 3 squared. So we first need to figure out what this function is. So what is that?
Isn't it it's like a sine function? Isn't it the inverse sine or something?
Like if it were like 1 over that thing
1 over,
squared,
yeah.
then the antiderivative of it would be an inverse sine.
See,
Yeah.
that was in my head.
Yeah. It's not wrong.
It's getting
This is not
there.
what we're going for.
We're close.
I mean,
Just not what we're
you're
going for.
essentially creating like a
Yeah.
shape-wise, I can't think of what I'm thinking of here.
So what if
Right.
Square root? The square root?
what if we said y
I mean,
is
just
equal to
shape-wise,
that?
It's going to be like
It's just like the.
your classic trick shape that you used for most of the damn semester.
Yeah.
And
So if we looked at it as y is this function, right? What happens when we square both sides? It doesn't, maybe that's not that helpful, but what if we put x and y together on the same side?
Circle.
Yeah. There you go. Circle with a center where? Center of 3. What? Yeah, so the whole circle just moves 3 units to the right, or to y'all's right.
3, 0.
3, 0, yeah. Circle, center, 3, 0, and a radius of
3. No. 1.
1. Yeah, remember this is your r squared over here. And that's the general formula for a circle of center HK with a radius. Square root of r squared, radius r. So we've got a circle. Is it a full circle centered at 3, 0 with a radius of 1?
Full circle.
Is it the whole circle?
No, because we're only doing a certain portion of this, right?
Yeah, which
4 to
portion?
3. Or 3 to 4.
From 3 to 4, yeah.
In the positive sector.
But if we looked at a circle from 3 to 4, centered at 3,
Catching like nothing, are we?
and goes from 3 to 4, radius 1, right? Would it be that whole circle? I thought I heard someone say. Someone said the top half. Who said that? Okay, how do you know it's the top half of the circle?
Because I said so.
Well, not necessarily because it's under the root, but because the root is
It's negative?
positive.
Oh, yeah.
No, y is the positive root, right? Y is positive.
So underneath is negative, so it's not positive.
Right, down here is where y is negative. Y is positive up here. So you get the top half of the circle from 3 to 4. If it were y equals to, right, if we work this backwards, if we started from here and worked this way, what we would actually end up with is that the circle has an equation plus minus square root. The plus is the top half, the minus root is the bottom half.
You aren't getting the whole top half though, right? You're just getting technically the top right quadrant. Because at 3,
The center's at 3.
y is equal to 1, your center's at 3.
Yeah, exactly. So then we have to go, we know this is top half of the circle, and I misrepresented the circle. But if its center is here and its radius is 1, then we're going out from 3 to 4 and from 2, like this. So we know we're dealing with this, right? Just as a general sense. But then we look at the integral from 3 to 4, we're only finding the area from 3 to 4. So yeah, that's equating to, we're finding here in this particular problem, the area of a quarter of that circle.
So you just figured that out and then pi r squared
Yeah.
over 4.
Yep.
Yeah.
What's right here, top half? Okay, terrible circle. And then we'll make a note here, the integral, we're going from 3 to 4 on that function. We're finding the area of a quarter circle. Again, if you forgot, oh hey, that's the top half of the circle, then what you would end up computing perhaps is the area from 3 to 4, you'd also get the area that's below, mistakenly computing the area of half a circle, but really all we're after in this integral is a quarter circle. If you have pi r squared is the area of a circle, we're just taking a fourth of that. Our radius was 1. So we'll write it again. The integral from 3 to 4 on the square root of 1 minus x minus 3 squared dx is the quarter area of the circle, which is just pi over 4. Anybody have any questions? And honestly, this is the easiest way to do that, is to recognize, if I think in Calc 2 you will talk about how you evaluate that directly. And it probably takes about 10 minutes to work that out by hand. So even when you determine methods to find areas or definite integrals, they're not always super efficient. Okay. I'm kind of shifting gears a little bit, looking at this particular figure. We're going to answer a couple of questions about it, just so we're kind of putting these pieces together. The first question is, what is the integral from a to b on this f of x? Does everybody agree that it's 12? The area bound by the function, the axis, and x equal a and b is 12. What about the integral from b to c?
Is it negative 10?
Negative 10, because it's below the x-axis, right? Negative 10. Okay, and what's the integral from a to d? 10. So how are we getting 10 for that one?
Add up the top, subtract it from the bottom.
Right, add up the top, subtract the bottom. So we have 12 minus 10, that's below, plus another 8, that's above. So it really just depends on the function and where you're looking at that function as far as the area is concerned, whether you're going to come out with a positive or a negative. But the idea is that when we compute this infinite sum from a to d on this function, we're coming up with the net area. We have the figure here, so we can say, like, if I just looked at the integral from a to b, then it's not really a net area because it's all above the x-axis. From c to d, it's above. From b to c, it's below. But when we look at a to d, then that's when we're actually getting a net area. And we can see that explicitly because we have the function or the graph of the function. Same thing with the last two geometric figures. If we didn't have that graph and we just know that the integral is equal to this number, the best we could do is say, well, that's the net area. There could be positive and negative contributions that are giving us that pi over 4 or whatever we come up with. We're generally not going to be looking at graphs to answer these questions. Okay. Does anyone have any questions about this?
For that D to A, would it not be? Didn't it say it was the bottom minus the top for that like original equation or the original definition? Did we say it was where was it? The sum. Oh, never mind. I was thinking that backwards. You're good.
Okay. All right, and these there's some properties that we have with definite integrals. Remember, a definite integral is just an infinite sum. So those properties of sums that we looked at do carry over to these definite integrals because they are one and the same. This we'll talk about. Maybe we can talk about number one once we get through section 5.3. But for now, it's presented as the integral from b to a on f of x. If we switch the limits of integration from b to a to b, then you just make the whole thing negative. So in the above example, if we went from, if we did the integral from b to a, we would have a negative 12 instead of a positive 12. The other property is that the integral from a to a on any function is 0. You're basically asking what's the area of that line. So if I just went from a to a, there is no area there. Okay, remember when we had the sum of two different things that were added or subtracted together? We said that we could distribute the sum to all of those things. The same is true for the definite integral. We can look at that as the integral from a to b on f of x dx plus or minus the integral from a to b on g of x. Properties of sums are properties of definite integrals, because that's what a definite integral is. And when we had a constant in front of the summation, we could pull that constant out and then compute the integral from a to b of f of x. So we would compute the integral and then multiply it by the constant. Or that's one way we could do that anyways. Does anyone have any questions at this point? All right. Okay, let's look at this last example here, and then we'll start talking about how do we evaluate these things. We're given the integral from 0 to 5 on f of x is 3, and from 0 to 7 on f of x is negative 10. I'm just compute a couple of these things. So example 1 says what we want to find the integral from 0 to 7 on 2 times f of x. What would that be? Negative 20. Do y'all agree? It's negative 20. So again, the way we're looking at that is it's a constant times a function of x, or the constant comes out. And we're given that integral. It's 2 times negative 10. or twice that area. Or if you look at it in terms of a functional transformation, you're stretching that function vertically by a factor of 2, so you're doubling the area. How about the integral from 5 to 0 of f of x dx?
-3.
-3. We switch the limits of integration. We just negate the result. The negative of 3 is -3. Okay, about the last one here, the integral from 5 to 7.
-13.
How do you know it's -13?
Because you know what 0 to 5 is, and you know what 0 to 7 is.
Okay. We know what the integral from 0 to 5 is, and we know what the integral from 0 to 7, right? We know this total was that negative 10? And we know that the integral from 0 to 5, maybe I should have put that below, was 3. So is it sufficient enough reasoning to say that since the area from 0 to 5 is 3 and the area from 0 to 7 is -10, that it has to be, what'd you say, Mike?
-13.
-13?
I thought it would be -7, since we have -10 from 5 to 7. That's -10, and then 0 to 5 is 3, so we add them.
Yes, so it's 3 minus a -10.
Okay.
Or we would say, well, since that area is below, we would say it's the net area from 5 to 7. It's actually neither. It's actually not. It's not the difference. It's not the sum. Because since we don't have a graph, so here's like a couple of scenarios could be. Because notice, like the integral from 0 to 7 just tells us the net area. So we know the net area from 0 to 7 has to be -10. And the only other piece we know is that the net area from 0 to 5 has to be 3, right? It doesn't tell us, if I look at that integral just from 0 to 5 being +3, all I know is that it has more area above the x-axis than below the x-axis. So even from 0 to 5, even from that standpoint, it could be that I have, I don't know, 10, an area of 10, and then an area of 7 below, right? That's just one possibility. How many different ways can you add up 2 or 3 or 5 things to give you 3? There's infinitely many ways. Like that's just one scenario, right? Another scenario, even just from simplifying this from 0 to 5, we could have a function that did something like this, right? And all of that could be 3. Does that make sense why we couldn't just take the 3 and the -10 and combine them and say that's the net area from 5 to 7? So those, again, you can come up with any other scenario you want. Go back here. Yeah, keep going. So the way we have to look at that is we can say, okay, the total area, the total net area from beginning to end. That total net area, if you will, if you want to think of it that way, doesn't that have to be the integral from 0 to 5? The net area from 0 to 5 plus the net area from 5 to 7? Out of all of the infinite possibilities we have, we know that this has to be true, that the overall net area has to be this net area plus this net area. So that's how we have to think of it, because it sort of eliminates the infinite number of possibilities. We're given this, That's -10, and we're given this, which is 3. We don't know this, but now we can find this. So it is, we're just going to subtract 3 to solve for our integral. It is -13, but you don't want to think of it as like a combination of 3 and 10 in any way. It just so happened to be that here, it is not, in general, not true that you can just combine those two things like that. So subtract 3, let's see. And solve for the integral. So we don't really do a whole lot with these things. There are some like this in the previous diagram in your homework. Just wanted to make sure that we talked about it. So, you know, we're kind of just connecting all of the layers here with the infinite sum, how the definite integral behaves, how we can compute it with geometry, and then we'll move on to look at it through the lens of the infinite sum. So does anyone have any questions here? So then we're going to talk about now how do you actually evaluate a definite integral. You know, one way we saw is through the geometric means, but it's not always applicable. So the generic approach is to use the definition of the integral, which is this infinite sum. So we're going to compute this infinite sum and say whatever that infinite sum is that definite integral. And the way we're computing that infinite sum, in order to simplify the computations, what we're going to do is say that our delta x's are still b minus a over n. This x star sub k, we're going to use right Riemann sums because the right Riemann sum was just a times k plus delta x. It didn't have a k minus 1 or a k minus half times delta x. So we're going to use right Riemann sums only, and it doesn't matter if you use right, left, or midpoint because we're filling that region up with infinitely many rectangles. So it's a moot point whichever Riemann sum you end up using, right? Might as well use this one because it's easier in a computational sense than the other two are. So basically what that boils down to is this is our working definition. We've just replaced our x star sub k virtually is the only thing we've replaced with the right Riemann sum. So f of a plus k times delta x. So that's going to be our working definition. When it asks you to compute a definite integral, we're actually going to compute this infinite sum here. So like we said previously, that f of a plus k delta x, that has to stay in front of the summation. Then all of that stuff becomes a function of n, and then we just take the limit as n goes to infinity on that function of n. So the k's stay as k's because they have to be summed in terms of n, and n stays as n because once we're done, we have to let n go to infinity. So it's not like we put infinity into the sum and work with it that way. It's just, in effect, what we're doing is we're computing a finite sum that comes out to involve n, and then we let n go to infinity. So that's the last thing you compute is the limit at infinity. So it gives you the net area, the exact net area, I should say. So that's our working definition of a definite integral. So I'll post these notes after class. You can copy them down later. I know it's a lot of stuff to write, which is why I kind of already had it here. So if you're not printing the notes, then you can just catch it on D2L later. and we'll at least start this example. So it says use the definition. Because in 5.3, what we're going to do is we're going to get a shortcut method to compute this, where we don't actually have to compute the infinite sum. Just like when we looked at derivatives, finding the difference quotient, simplifying the difference quotient, and then letting h go to 0, it's a super tedious problem to find derivatives all the time. So we then looked at shortcuts on how to find a derivative. Or we're going to look at shortcuts later on how to compute this. But for now, it says use the definition. So there's our fx star as our right Riemann sum, a plus k delta x evaluated at f times delta x. So we're just fitting things into that summation. We're given f of x as x squared. What is delta x in this example?
People are saying, can we figure it out? Because we can figure it out without knowing anything about the subintervals.
Right. So notice we're not given the number of subintervals, because what are we going to do to the subintervals at the very end? We're going to let them approach infinity, right?
Is it just 0 in this case? Because you're...
No, it wouldn't be 0, because we don't have 0 rectangles, right? We have infinitely many rectangles, but we have to let that number go to infinity. So that n here now, since we don't have a number of specified and we're looking for an exact area, it just has to stay as n. So delta x is 2 over n. So that's really the first thing you want to find, right? We can't find a plus k delta x without delta x. We couldn't find f of a plus k delta x without delta x either. So we need to find delta x first. Found that little thing. Then we're going to figure out what a plus k delta x is. Because this is our x star. That's going into the function. So our a is what?
So just 2k over n.
0 plus k times delta x, which was 2 over n, which, right, it's just 2k over n. Let me write that in a different color. Okay, so the a plus k delta x then is placed, or evaluated, the function is evaluated rather at a plus k delta x. And our function is just the squaring function, so it's going to just take the input as 2k over n and square that. We're just going to expand that out. We're going to write that out as 4k squared over n squared. And then that's it. That's the two pieces. 1 and 3 are the two pieces of information that we need to put in front of that infinite sum. So that's what we're going to do now. We're just constructing the sum from k equals 1 to n, and then we're going to let n go to infinity. The 4k squared over n squared needs to be summed. So that's f of x star, and then we have to multiply by our delta x. Everybody all right with where we're at? Again, the limit only operates on things that involve n. The sum only involves the variable k. So the way, this is our this is kind of where we want to be after we've kind of put everything together. Then we compute what this actually is. So we're going to look at this two ways. We're gonna look at this as kind of through the lens of the summation formulas from Theorem 5.1, and then I'll give you a handout that'll maybe simplify this a bit. So method 1. Is Theorem 5.1. So we're going to have the limit at infinity. We just, in front of the summation, we just want the k part, right? Because the theorem is presented as the sum of just k squared. So that's what we want if we're going to use Theorem 5.1. The 4, the n over the n squared times the 2 over n, that can all be pulled out in front of the summation because it's just a constant times that sum. So we have 4 times 2 over n squared times n. And then, of course, the sum goes, excuse me, sum goes from 1 to n. Is everybody all right with that step? So then all we're going to do is address what this summation is. The theorem 5.1 tells us that the sum of k squared up to n is going to be what? Here, let's go back. Oops, there we are. For the squares up to n plus 1, 2n plus 1 all over 6 is what that is. So notice what we have in effect is we've got a limit at infinity and we've got a polynomial over a polynomial involving n. So we could multiply all of this stuff out, but limits at infinity dictate that really all we have to do is look at the leading term of the numerator and the leading term of the denominator. So let's just write it out that way. To evaluate that limit. As n approaches infinity, what would the leading term on the top be? But they're all multiplied together. Yeah, so they would have to be in there, right? You've got an n times a 2n times an 8 all on top. Yeah, 16n cubed, does everybody agree? If you don't multiply all of it out, it's going to take you a little bit, but you will have definitely 16n cubed as the highest degree of n on top. And on bottom, it's just simple, it's just 6n cubed. So what is that limit, 16n cubed over 6n cubed? Do what? Sorry. Yeah, it's just 16 over 6. And that is the net area, the exact net area. So since we actually haven't talked about the other theorem, I'll hand this out next time, or do y'all want it now? Okay.
Is it online too already?
Yeah, I believe it's on D2L.
Since it's here.
Yeah, why not?
We'll talk about it next time, so if it doesn't make a whole lot of sense, that's fine.
Maybe that's about 7.